Analyzing a function for its symmetry is useful in calculus and beyond. In fact, symmetry plays a central role in mathematics. So let's get started with some basic definitions. Here we have three functions. The first one here is symmetric about the y-axis, and it basically looks like a parabola that perfectly straddles the y-axis there. And what that means is anytime there's a point xy, then the point negative xy also is included in the graph. These are very nice functions. We see them often in math, so often that we give them a special name. We call them even. These are even functions, right? Because we don't want to sit around saying symmetric about the y-axis all day. It's a little much to say. So let's just call those even functions. All right, moving on to the next one here. Here we have essentially a sideways parabola that straddles the x-axis. And we say that these are symmetric about the x-axis. And here, anytime a point xy is included on the graph, the point x comma negative y is also included in the graph. Now, for these, we don't have a special word like even or odd because those only refer to functions, and note that this sideways parabola technically is not a function because it fails the vertical line test. Moving on to the third example, here we have something called symmetric about the origin, or symmetry about the origin. And what that means is anytime you have a point xy included in your graph, the point negative x comma negative y is also included in the graph. This is another kind of function that shows up all the time. It shows up so often we give it a special name. We call this an odd function. Odd. Now, a slightly faster way of looking at these functions or thinking about them is as follows. Back to our even function, if you can fold this along the y-axis, so imagine folding this like a piece of paper along the y-axis and your points would line up exactly, then that would be an even function. So note we could have a point up here, we fold it across, it ends up over here, it's an even function. For odd, it's similar, but it's a little confusing because they say symmetry about the origin, so you may think, oh, we fold it somehow diagonally, but it's actually a two-step folding process. We fold once across here like this, across the y-axis, and then our second fold brings us down across the x-axis. And if it's an odd function, that point will line up exactly on the graph again. So we go 1, fold it into this, I guess, quadrant 2, and then 2, fold it down, and we're right on top of a point. And that would happen for every point in this graph. So that's another way of thinking about odd functions. Well, oftentimes we don't know what the graph of a function even looks like. So we need a more analytical definition of even and odd. And here it is. If a function is even, then f of negative x is the same as f of x. Meaning that if you replace x with negative x everywhere in the function and get the same function back, it's an even function. For odd, we have f of negative x equals negative f of x. That means if you replace x with negative x everywhere in the function and you get a perfect negative version of the function back, it's an odd function. Let's use this analytical definition to try an example. This example asks us to determine whether the functions are even, odd, or neither. For part A, we have f of x equals x to the fourth minus 2x squared minus 20. So what we do here is we plug in negative x. So f of negative x is, okay, so that's negative x quantity to the fourth minus 2 times negative x quantity squared minus 20. But since 4 and 2 are even, the negative x's just become x's, so that gives us x to the fourth minus 2x squared minus 20, and we are right back to f of x again. So this function is even. For part B, we have g of x equals x cubed minus 3x plus 1. So we do the same technique again. G of negative x, all right, so we have negative x cubed minus 3 times negative x plus 1. Well, the negative lives on through this exponentiation here because 3 is odd, so this becomes negative x cubed. Negative times a negative is a plus 3x plus 1. Well, this is not equal to g of x because it's different, but it's also not equal to negative g of x. right? Because of that pesky +1 business going on here. So part B is neither even nor odd. Moving on to part C, we have h of x equals 1 over the quantity x cubed minus x. So hitting it with our test again, we have h of negative x equals, all right, so this is 1 over the quantity negative x cubed minus a minus x. Okay, well this simplifies to 1 over negative x cubed plus x. So let's factor a negative out to the front here. This becomes negative 1 on the top over, this becomes now x cubed minus x, which is simply all minus h of x again. Okay, well that is our definition of an odd function. So for part C we have odd. Now I won't do this here, but if you want to gain a little more of an intuition about what's happening here, I recommend graphing all three of these functions in Desmos so you can see the actual symmetry of these things happening visually rather than this completely analytical approach. It gives you a little bit deeper of an understanding.